Here's example 4 with using the first derivative test to find all local extrema of a function. So in this one we're going to find all the local extrema of z equals 5w divided by the square root of w minus 2. Okay? So step 0, find the domain of our function, whatever we're calling it, in this case z. So step 0, find the domain. Now in this case we do have a domain restriction to worry about. So in examples 1, 2, and 3 we didn't really have that, but now we do. So remember, domains, your domain restrictions are you can't divide by 0, you can't take square roots of negative numbers, or any even root really, square roots, fourth root, sixth root, etc. Can't do that with negative numbers, but 0 is okay, right? And you can't take logs of 0 or logs of negative numbers. So there's no logarithms here, so nothing to worry about. But we are dividing, so we have a denominator, and we also have a square root. So here, w minus 2 is inside of the square root, so w minus 2 has to be greater than or equal to 0. But also, we're dividing by the square root of w minus 2, so anything we divide by can't be 0. So this sits inside of a square root, so it has to be greater than or equal to 0. This whole thing is in a denominator, so it has to be not equal to 0. So here, just add 2 to both sides, so w is greater than or equal to 2. But here, so it says not equal to, but we can treat it just like an equality, so we can pretend it just says equals. But anyways, and what I mean is, just solve it like we would solve a regular equality. So square both sides, and we get w minus 2 not equal to 0. 0 squared is just 0. Add 2 to both sides, so w is not equal to 2. All right, so basically, w is greater than or equal to 2, and w is not equal to 2. So remember, both of these have to be true at the same time, because we have both of these restrictions happening. Both these things are happening, square root and a denominator. So both of these have to be true together. So w has to be greater than or equal to 2, and w has to be not equal to 2. So if you want to draw a number line real quick, you don't have to do that, but here's 2. Okay, so w has to be greater than or equal to 2, all right? But also w is not allowed to be equal to 2, so we're going to toss 2 out of there, okay? So basically, both of these together just means w is greater than 2. So that's our restriction here. So greater than or equal to 2 and not equal to 2 means just greater than 2. So that's our domain restriction. W has to be greater than 2, strictly greater than 2. So let's get rid of all this and just write that down. So we'll put capital D for domain. So the domain is the interval from 2 to positive infinity. Or in other words, remember, just W is greater than 2. So that's our domain restriction here. And remember, we care about the domain because in order for a value of x, or in this case a value of w, in order for that to be a critical point, it has to be in the domain. So if we find a critical, or a potential critical point, so to speak, that's outside of this domain, then we just toss it out, because it doesn't matter. So anyway, that's step 0. Now step 1, find all the critical points of the function. So we just take the derivative of this guy, set the derivative equal to 0, solve for w, and we also find out what values of w make the derivative undefined. Okay, so let's just go ahead and take that derivative. So z is a function of w, so it's really going to be dz dw, dz dw, derivative of z with respect to w. But just for, just to keep it short, let's just write z primed. So z primed equals, so we're going to have a quotient rule thing here, right? Bottom and a top, so we have a top and a bottom. So quotient rule says the derivative is bottom times the derivative of the top. Okay, so here's the bottom, it's the square root of, let's be a little more neat with that, sorry about that. Bottom is square root of w minus 2. Okay, so bottom times the derivative of the top. Now the top is 5w, so its derivative is just 5. Okay, bottom times derivative of the top minus the top times the derivative of the bottom. Now the bottom is the square root of w minus 2, so what goes here is the derivative of that. So let's actually come off to the side and work with that. So root w minus 2, remember that's the same thing as w minus 2 quantity to the 1/2. Okay. Now if we want to take a derivative of that, then we're going to do a power rule here, right? So it's going to be 1/2 times the quantity w minus 2 to the negative 1/2. And then technically there's a chain rule thing happening, so chain rule says now multiply by the derivative of w minus 2, but the derivative of w minus 2 is just 1, or technically 1 minus 0, but still just 1. So this is what we have, 1/2 times w minus 2 to the negative 1/2. Okay? Now, remember, negative exponents, they go into the denominator here and become positive. So this is 1 over 2 times w minus 2 to the positive 1/2. And remember, 1/2 in the exponent means square root. So this is 1 over 2 root w minus 2. Okay, so that's the derivative of the bottom of z, of the denominator of z. So just to recap real quick, derivative is bottom times derivative of the top minus the top times derivative of the bottom, which we just found out is this mess right here. So that's the derivative of the bottom. So we're going to take that and put it over here. So it's 1 over 2 root w minus 2. All right, so bottom times derivative of the top minus the top times derivative of the bottom, all divided by the bottom squared. So root w minus 2, that whole thing is squared. Okay, now let's get rid of all this over here to make some room for later. All right, we'll come back over here. So let's go ahead and simplify this a bit. So let's see. This is just going to be 5 root w minus 2, and then minus, let's go ahead and write this as 5w over 2 root w minus 2. So 5w goes on top, and then 2 root w minus 2. All right, and then all of that is over, so square root of w minus 2, if you square that, the square and the square root cancel, and they simplify and you just get w minus 2. So that's not bad, right? Now, what do we have here? We have a complex fraction. We have a big old fraction here and then another smaller fraction sitting inside of it. So actually, what we have to do here is ignore the bottom for now. Let's get a common denominator up here. So that's one thing we could do, get a common denominator. Or we could look at this whole thing and say, okay, I want to get rid of this denominator here. So what we could do is take the entire top, let's take the entire top and multiply it by this denominator. So if we do that, then we have 2 root w minus 2. All right. Now, because we multiplied the big top by something, we have to multiply the big bottom by the same thing. So 2 root w minus 2. Okay. So multiply the top and the bottom by the exact same thing. So this is the exact same process as, ignoring the bottom and getting a common denominator. But for me anyway, it's a little bit easier to think of it like this. It might be for you, or you might prefer the common denominator method, in which case you take this, just this guy, and multiply it by 2 root w minus 2 divided by 2 root w minus 2. And you'll eventually get the same thing, but I just think this gets you there a little bit quicker. But anyway, multiply the top and the bottom by the same thing and you're good. So let's zoom out just a bit here, and let's go ahead and simplify this. So there isn't really enough room here, so we're gonna have to come up a bit over to here. So if we bring this up here, this equals, so now we're just going to take 2 root w minus 2 and distribute it to everything here. So 5 root w minus 2, 5 root w minus 2 times, let's keep the colors the same for now, times 2 root w minus 2. All right. So we have 5 root w minus 2 times 2 root w minus 2, just distributing. And then over here we have minus, okay, minus now this whole mess times that. So 5w over 2 root w minus 2. And then times 2 root w minus 2. All right. And then on the bottom, we still just have the quantity w minus 2 times 2 root w minus 2. So this is w minus 2, that quantity, times 2 root w minus 2. Okay, so that's what we have here. Now, let's see. So let's go ahead and simplify this up here. So again, all we really did was we took this on top and distributed it, and then on the bottom we actually didn't really do anything. But on the top we distributed. So first term times that minus second term times that, and that's what we got up here. So now let's zoom back in a bit. All right, and let's go ahead and simplify this now. So this equals 5 times 2 is 10. Square root of w minus 2 times square root of w minus 2 is just the quantity w minus 2. So be careful because the 10 is being multiplied by the whole thing, because it's really, it's 5 times this times 2 times that. So really the w minus 2, if you square that, multiply by itself, then that quantity is going to be what's multiplied by everything else. So 10 times the quantity w minus 2. And then over here, this is nice. This is why we did what we did, so that this will cancel here. 2 root w minus 2 and 2 root w minus 2 cancel, and then we just have minus 5w. That's beautiful. All right, now on the bottom, 2 times, so if you have w minus 2 times square root of w minus 2, actually let's just go ahead and leave it like that for now. W minus 2 times square root of w minus 2, because it's actually not really going to matter. Okay, so now we distribute on top. Let's zoom back out just a bit. So on the top we're going to have 10w minus 20. So 10w minus 20, and then minus 5w. Still from this 5w here, and then 2 times w minus 2, times the square root of w minus 2. Alright, so 10w minus 5w is 5w, so then this equals 5w minus 20, all divided by 2 times w minus 2 times root w minus 2. Alright, so this is our derivative here. So yeah, now w minus 2 times root w minus 2, let's come off here and just make a side note real quick. So w minus 2 times root w minus 2. Remember, w minus 2 is the same thing as root w minus 2 squared, right? So this, just this by itself is the same thing as that root w minus 2 quantity squared. And then we're multiplying by this. So what do we have here? We have root w minus 2 squared times root w minus 2 to the first. So that's root w minus 2 cubed. And remember, square root is to the 1/2 power. So this is w minus 2 to the 1/2. And then we're cubing it, so it's really to the 3/2. So in other words, w minus 2 times root w minus 2 is just w minus 2 to the 3/2. So if you really want, we could write the derivative as this equals 5w minus 20 over 2 times w minus 2 to the 3/2. But for what we need to do with it, we don't really need to write it in that form. But if you want to, that's totally fine. If you don't want to, there's really no reason not to. Or no reason to do so, I guess. No reason either way. But anyway, this is our derivative here. So let's keep it with this form. 5w minus 20 over 2 times this mess here. So let's get rid of all this and just put that over here. Alright, so this is 5w, we just found out it's 5w minus 20 over 2 times w minus 2 times root w minus 2. So we see this process can be kind of long and a little bit messy sometimes depending on what kind of function we have. Right? But still, the process is always the same. It's always these 4, maybe 5 steps, I guess, to follow each time. So we're still on step 1, actually, find all the critical points. But really, this is probably the worst of it. Or the worst of it's probably over. Anyway, now we find out, okay, where's this derivative 0 and where is it undefined? Well, let's talk about where it's undefined first. So it's undefined when the bottom is 0, which happens when w is 2, okay, from either of these guys, when w is 2. But it also happens if w is less than 2. Okay, because if w is less than 2, then we're taking square roots of negative numbers. So actually, z primed is undefined. Here, the derivative doesn't exist when w equals 2 or is less than 2. So when w is less than or equal to 2, right? So actually, the derivative is undefined at all these values. But remember, the domain is w has to be strictly greater than 2. So we have all of these places, an infinite number of points where the derivative is where the derivative is undefined, but not a single one of them is in the domain. So we could just forget about all these, right? And that's good. That's great. So again, infinitely many points where the derivative is undefined, but not one of those points is in the domain. Okay, so we can just forget about those. So now we only care about where's the derivative equal to 0. So we just take this guy and we set him equal to 0, and we just solve. So we have a top and a bottom equals 0. Remember, if you have a fraction or any kind of fractional thing like this equal to 0, that only happens when the top is 0. So really, we only care about when is the top 0. So that's just a property for fractions or rational functions or rational type functions. So this isn't exactly rational because this isn't a polynomial down here. But anyway, just tiny little details. So anyway, 5w minus 20 equals 0. And, you know, a bunch of different ways to think about it, but you're just going to end up with w equals 4. So add 20 to both sides, divide both sides by 5, w equals 4. So this is the only value of w that makes the derivative equal to 0. All right? So this is our only critical point. And that's step 1, find all the critical points of the function. And this is the only one. So after all that mess we did, we only have one critical point. How about that? All right, so let's come up here now. And now we're going to do step 2, make a sign chart. So make a sign chart. That definitely didn't have to be that big. So we'll put 4 here. Okay. So remember, always label the sign chart. So the function is z, its derivative is z primed. Sign chart is always for the derivative, for the first derivative test. So it's z primed. Okay, so now that's it for step 2, make a sign chart. Now step 3, determine the sign of the derivative in each interval. So this is negative infinity to 4, this is 4 to infinity, so we just pick one number from each of these intervals. So, oh, you know what else too? What we should do, since the domain restriction here is w is greater than 2, let's also section off here. Here's 2. And then we're just going to forget about this stuff over here. So that's all gone. We can actually just erase it, I guess, but we're just going to forget about that. So when we choose this interval here, we actually can't go less than 2. So actually the two intervals we have are from 2 to 4 and from 4 to infinity. So don't forget about the domain restriction here, like I almost did. But anyway, 2 to 4 and 4 to infinity. So we pick one number from each of these intervals, and we evaluate the derivative at that number we pick. So between 2 and 4, a good number to pick is 3. So z primed of 3 equals what? Well, let's go back over here. So here, it actually might be helpful to have the derivative in the other form where we had w minus 2 to the 3 halves. But you know what? It's actually not going to matter that much. So let's not worry about it. But anyway, here's our here's our first derivative here, 5w minus 20 over this mess here. So z primed of 3 is going to be 5 times 3 minus 20. So let's write that. 5 times 3 minus 20 divided by 2 times w minus 3 times the square root of w minus 3. 2 times, w is 3, so this is 2 times the quantity 3 minus 2 times the square root of 3 minus 2. 3 minus 2 times the square root of 3 minus 2. Alright, I thought what I was saying didn't make any sense. Okay, so anyway, 5 times 3 is 15. 15 minus 20 is negative 5. So we have negative 5 divided by 2 times 1. 3 minus 2 is 1. 3 minus 2 is 1. Square root of 1 is 1. Anyway, we just have this. So this is negative 5 over 2. Alright, which is less than 0. So what we just found out is that when w is 3, the derivative z primed is negative. Right? So we go back up here to our sign chart. Let's label with a different color. So negative derivative in here. All right. Now we're going to do z primed of 5. Okay, we're just going to pick 5 from this interval here. Again, it doesn't really matter, but you know, we just pick any number from this interval. So let's just pick 5. So z primed of 5 equals, well, let's see. We're going to go back to our derivative here. So it's going to be 5 times 5 minus 20. Because w is 5 now. 5 times 5 minus 20. And let's get this right this time. So now we have 2 times the quantity 5 minus 2 times the square root of 5 minus 2. So this is 2 times 5 minus 2 times the square root of 5 minus 2. All right. So let's simplify just a bit. 5 times 5 is 25. 25 minus 20 is 5. 5 over 2. So this 2 is still here. And then 5 minus 2 is 3. 5 minus 2 is 3, square root of 3 is square root of 3. So actually, everything here is positive, right? 5 is positive, 2 is positive, 3 is positive, square root of 3 is positive. So just a bunch of positive numbers being divided and multiplied. So everything is positive. So this whole thing is positive. So if we come back up here, we know the derivative is positive in this entire interval. All right, so that was step 3. Determine the sign of the derivative in each interval. Okay, now step 4 is apply the first derivative test to find extrema. So first derivative test, we apply that, we see, okay, Z primed is negative, so that means Z is decreasing. Okay, negative derivative means decreasing function. Positive derivative means increasing function. So Z primed is positive means Z is increasing. So decreasing function, increasing function. First derivative test tells us we have a local min right here at when when W equals 4. So that's where it happens. Now we just have to figure out, okay, what is the actual value? So now to figure out what the value is, we take this value of W and put it back into the original function. So remember, always be careful with that. Always put it back into the original function. Okay. Because we're talking about mins and maxes of this function Z. So we just found out where a local min occurs. Now to figure out what it is, we put the value of W, which is 4, into this function here. So let's go ahead and do that. So Z of 4 equals 5 times 4 over square root of 4 minus 2, because it's 5W over root W minus 2. So this is 20 over root 2. All right. So, you know, if we rationalize the denominator, we're going to have times root 2 over root 2, and then that's going to be 20 root 2. Root 2 times root 2 is 2, so this is 20 root 2 over 2, which simplifies to 10 root 2. So normally, you know, when you get to a calculus class, rationalizing the denominator is kind of a thing of the past, not really something you do anymore. But in this case, it does simplify it a little more. So this is a little more simplified than that. But anyway, the main point here is this is what the local min actually is. So we just found out where it occurs, which is at W equals 4. And now we just found out that the local min is Z equals 10 root 2. So let's go ahead and write that down. And that's actually pretty much it for this example then. So local min at, so our variables are not x and y, but they're z and w. So local min at W equals 4 is Z equals 10 root 2. And there actually are no local maxes, right? So this is the only thing happening here, so there's no local maxes. And 2 doesn't count as a local max or anything really, because 2 is just where the domain restriction happens. So W has to be strictly greater than 2. So that's just here to mark off the domain, basically. So only critical point was 4, and that's where we have a local min. So our answer is local min at W equals 4 is Z equals 10 root 2, and there's a no local max. No local max. And that's pretty much it for example 4 with the first derivative test.